Okay, so going to tell you about my opinions about a sort of and some results about doing sort of anonymous credentials. All right. So, but first, since I work for Polkadot for the Web3 Foundation doing Polkadot, I want to advertise Substrate a little bit, which is our sort of platform for building blockchains. So people here will probably be interested in doing cryptography. So of course, since in Substrate, since you're using WASM, of course you can just build any cryptography you want in the WASM. However, for certain kinds of really highly optimized stuff, that can be as much as 10. Things can run as much as 10 times slower in WASM than in native. So, okay, we will be adding to Substrate, or we have already added, but they're not actively deployed in Polkadot yet, but they will soon be. Something vaguely like these elliptic curve precompiles in Ethereum. However, sort of some cautions I want to give about the Ethereum approach is that it's actually quite inflexible. There's various stupid things that happen, like your Gros16 would need 4 pairings, various other things. It doesn't actually mesh very well with being able to do your own stuff with the curve. What we've done instead is, since you're compiling everything from Rust, basically we've just designed the host calls, the equivalent of these precompiles, to mesh very nicely with the kinds of calls that every other elliptic curve ecosystem, tooling uses. So there's separate calls for like the multi-scalar multiplication and the Miller loops and things like this. So this means that you can just take your Rust code and then build it and just swap out the elliptic curves and it'll compile nicely for Substrate. And literally the kind of code diff you're looking at is something like that. So the advertisement here is basically that you don't have to re-implement stuff in something like Solidity. You can just use something like ArcWorks or some other, or adapting these crates, some other kind of Rust elliptic curve libraries, and everything will work very nicely. So a little bit less overhead if you're trying to build something. Okay, that's just a very quick bit of publicity of technical sort of publicity for people who are trying to quickly get out stuff. And anyway, advertisement for Substrate. Okay, so what I actually want to talk to you is about these ring VRF things. So everybody here probably knows what a ring signature is. It just proves that the signer exists in some publicly specified list. Well, the list may or may not be public, but somehow the commitment to the list is public. And this is used in various things like deniable key exchanges and for online money stuff, at least the blockchain versions of that. And there's many different types of these things with various different performance computations or considerations. But basically, generally speaking, they're fairly heavy. Like there's you really have to do something to be dealing with this list, as opposed to something like a group signature where you have some kind of certifying entity, and you're essentially checking a certificate in zk. All right, so the other thing I want to tell you about, so I'm going to be talking about ring VRF. So the other thing I want to say is, what is the verifiable random function, or VRF? So these are they basically prove evaluation of a pseudo-random function whose 2 inputs are the secret key of the signer and some piece of the message being signed, some fixed piece of the message being signed. What do these look like? The simple one that everybody uses here, just the verification equation of it just looks like 2 Schnorr signatures where the C's and the S's are the same. That gives you something that does what's called a discrete log equality proof between some kind of point that the prover has claimed, which is going to be they've claimed that it's something hashed to the curve times their secret key and the public key. So this proves that both of these are multiplied by the same secret key. And then this guy hashed this makes this thing a random function of the secret key and the input message. And then when you hash it again with the input message, you get something that's actually reasonably close to pseudo-random. Okay, so I'm not going to talk too much about how VRFs actually, I'm going to talk a tiny bit about VRFs because there's a cute trick that we use. But okay, So ring VRF, what is it? It's a ring signature that also is a VRF. It means that you're proving some pseudo-random function where you don't know now, the verifier doesn't know who the signer actually is. They don't know the public key of the signer, but they will know from the proof that the output this ring VRF is claiming is this pseudo-random function of the real signer's secret key, and that secret key corresponds to a public key that's in the list. That's the goal. All right, so a tool, well, okay, so what are you going to do with these things? Well, one thing, if you want to think about VRF protocols, you can often take any VRF protocol and you can think of it in terms of like a card game. Basically, usually the way the VRF protocol works is the public key that has been like put on the chain or wherever, or in some certificate scheme or something, the public key acts like some kind of commitment, and then you can pull out using the VRF, you can pull out sort of very dynamically kind of open different kinds of views into this commitment. Or that's one way to think about it. So you can think about it as like, okay, we have an infinite deck of cards and everybody agrees on some randomness, and then that randomness concatenated with 1, 2, 3, 4, 5 or whatever determines my hand, and when I want to play one, I simply sign that input and maybe some auxiliary thing, and that corresponds to playing a card. So what is a ring VRF good for? So one thing you can't do with a regular VRF, you think about Cards Against Humanity, the way you play it. You play the cards face down, and then there's an anonymity layer where the cards are shuffled, and then they're flipped face up. So with a ring VRF, you can go through an anonymity layer like Tor, and you can play the card, and it's now anonymous who's playing. So you can play Cards Against Humanity, which you can't do with a regular VRF. No, infinite deck Cards Against Humanity. Okay, that's one example, and we'll get something with that. Okay, so here's a very quick, slight alteration on that EC-VRF that I showed earlier. Essentially, all I'm doing is I'm adding to the secret key, I'm turning the secret key into a Peterson commitment I'm turning this public key, I'm replacing it with some Peterson commitment to the secret key by adding this blinding factor times some independent generator. And then I just add something, and then I just add kind of a second piece times this same thing to one of these two verification equations. And what this does is it just opens basically what it's doing is it's saying, okay, I have a commitment to this secret key, and now I don't know what the secret key, I don't know what the public key is, but I'm going to prove that this out guy is just times the secret key. So then I get something hashed to the curve times this output, or times the secret key. And this will, is this kind of thing going to de-anonymize me? Well, I have to get this commitment to the secret key in some way. That I'll talk about in a minute. But this out thing will de-anonymize me if and only if the message is the same input message appears in some other context. So it gives me this is all right. So this is basically going to be how we get a VRF out from some other kind of zero knowledge proof that gives me a Peterson commitment to some secret. All right, and of course what you can tell here is that this thing is very, very cheap. It's about the cost of 2 Schnorr signatures. All right, so what our goal is, so the rest of, I said ring signatures are generally pretty heavy. The rest of the ring signature is the thing that's going to be the problem, the thing that does basically the database lookup into the ring. And so what we want to do is we want to make that cheap. So all right, let's look at Gross16. So this is the Gross16 verification equation. So X is these public inputs. And what I'm going to do is I'm going to define, so the Gross16 itself, the proof is these ABC guys. And the things in brackets are the toxic waste. They're kind of fixed constants. But you don't know what the alpha, beta, gamma, delta are. So what I do is I want to make a snark that does something that sounds really stupid. it opens, it does some kind of database lookup for the public key in the ring. This is the very expensive part. And then what it does is it just proves that that some secret key corresponds to that public key, and then it reveals the secret key. So that's what this Groth16 is doing. This sounds very useless because I just have a ZK proof that just reveals my secret key. But what I'm going to do is, okay, so I'm going to define this thing, we call it special G, or specialized Groth16. And what it does, so the idea is here is we have some inner Groth16 that's going to leak secrets, but we're going to change it. What we're going to do is we're going to take some independent point K, and we're going to add it to the trusted setup, and we're also going to add the gamma over delta, these are toxic waste elements, to the trusted setup. So now what I can do is I can add into the public input, I can add a blinding factor times this K guy. And so the black part here is the usual re-randomization procedure for Groth16. And if what I do instead is I add this one other deformation to the C part, then when I re-randomize my Groth16, I alter the public input by this B as well. So this means that I can prove once this lookup that says, here's my secret key from this database, and then I can keep getting different Peterson commitments out of it. So what I get out of this is a ring VRF whose marginal, so I got to prove this lookup once, but now the marginal signer cost is 8 G1 scalar malts and 2 G2 scalar malts, which, if you think about the usual kind of costs of ring signatures, this is incredibly cheap. I mean, usually we're, okay, and it doesn't really matter how big the ring is here. Now, of course, if we're in some blockchain context and the ring keeps changing, that can be an issue. So this is what we're calling zero-knowledge continuations, where you somehow use the Groth16 re-randomization or something like that. And so there's various, I'm not going to go into the technicals here, but there's various other things you could do. You could, for example, have a simpler Groth16 that just does this mapping from a public key to the secret key, and then actually do the ring lookup in something else like calc or calc plus, which are basically building little kinds of zero knowledge lookups from KZG. Anyway, that would give you some extra kinds of side channel protection if the ring is changing a lot. Another thing you can do is you can add a kind of a revocation list to the thing, and you can prove in ZK that your key so there's a database you do a lookup into, and then there's a more efficient lookup done in this calc, not exactly in the calc style, but in a vaguely similar way into some. Into a revocation list, and the revocation list is much smaller than the whole ring. Okay, anyway, so this is some stuff we're working on. I'm being very slow at implementing it, but it's moving. How much time do I have? Yeah. So 10 minutes. Yeah. Okay. So now, okay, why? Okay. So there's a lot of stuff is being discussed now about anonymous credentials. In particular, there was this whole W3C DID effort, like these distributed identifier things. And so by and large, there's a number of problems with that, and I want to explain why I think these ring VRFs give a better setting. So okay, what if we use, mostly when people talk about anonymous credentials, so these ring VRFs, they give you a mapping from some kind of input to an output that's supposed to be unique in the context of that input. And so, but they don't actually really tell you anything about the user other than this kind of uniqueness property. So normally when people talk about anonymous credentials, what they're talking about is attribute-based credentials. And so the usage, it looks something like the browser or whatever validates some TLS cert, and then it gets some attribute requests, and then it reveals these things. So problems with this is these attributes are already So a thing that Brian Ford points out in his like proof of personhood papers and other things is that these attributes are already unnecessarily leaky. Like you don't need to know the nationality or something of a user most of the time to be able to, I mean, most websites actually just care about not being spammed. So this is already unnecessarily leaky, but this is the kind of thing people are wanting to deploy. And of course, the attributes leak across domains, which is not great, and various other things. So what I would like to suggest is that whenever we have some kind of attribute, something that's going to prove something about the users, what we should really be saying is that before the user even gets asked to reveal something, there should be some certificate check that says this website is allowed to ask for your age. And that if the website isn't, there needs to be an entire certificate infrastructure there that just says you're not even allowed to ask, or at least not allowed to ask in any kind of provable way. And if we have this kind of thing, then the stuff like the ring VRFs become much more efficient because from a business perspective, because I don't have to ask to be allowed. All I do is put my public key into the input to the VRF, and then nobody else can ask the same questions as I can ask. So, all right. Yeah, so that's the ring. The thing here is quite a bit simpler if we want to use it as an identity system. So anyway, so the point is basically it's a much safer identity system. Maybe that I didn't make that as clearly as I should, but okay. One of the things, it's a bit more, it's not quite, so if we want to use a ring VRF as an identity system, there's actually a bunch of variations we can do here. One of them is we can say that instead of just the input being like site.com or the public key of site.com, then we can have the input be like the public key of site.com and the month. And now what happens is that the user's identities change every month. But I could provide proofs for multiple months at a time to establish a continuation. And now if a user wants to go away from a site and come back, they just go away for a month and then come back, and there's no linking. So this gives you like kind of a temporary blacklisting thing instead of a permanent blacklisting. So you can design various. Anyway, the point is you can design, even from this very limit, it's just a VRF or multiple evaluations of a VRF, you can get a fairly flexible like usage specification out. All right, so now since this is a blockchain talk, or this is a blockchain meeting, so the question is, can we get payments from these things? Because we have such an efficient ring signature. Well, the answer is no, because when you do a payment, you're usually looking up something once, and the whole thing I was doing is I was amortizing the cost of this lookup. So you don't really get a payment out unless you could do something, but I mean you can do things, but it doesn't get the same kind of efficiency that it does as an identity system. But there is one big exception. So okay, there's climate change. We're headed for plus 3C by 2100, but plus 4C says that Will Stephan and people say that the tropics are uninhabitable and the carrying capacity is at most 1 billion people at plus 4C. At some point we're going to start having shortages, and it'll be in different places at different times. What ring VRFs are very nice for is when you want to have basically an anonymous rationing system, because I can do so. Like we had a mustard shortage in France 2 years ago, so you can have something like the input message is France mustard, and then the week, and then the number, and then a counter which goes up to the number of mustards you're allowed to buy that week. And now we do exactly the same sort of thing that we do with anonymous money. We take these outputs and we use them as nullifiers, and but now we get to throw away the nullifier after a week or a month or whatever it is, because they don't have to live very long. It's just some kind of very short-lived thing. So what we as blockchain people care about for this is that if we can use these things as kind of, basically if we can use it for rationing, well, we can also use it for, there's a lot of stuff we want to be able to let people do for free on blockchains, like in particular play games. It's one of the major problems with the whole industry is that there's not a free tier of service. And with this kind of thing, you can provide a free tier of service that's, the crypto is extremely efficient. You're still doing pairings, but you know. One other thing, okay, so if we imagine that, still talking about the ration cards, if we imagine that, you know, we want an EU ration card system or something like this, generally speaking, humans have not been terribly great at not having, so of course the crypto is sound, but oftentimes when you have a certificate infrastructure, somehow in there it gets compromised, either by other nation state actors or just whatever. So there's a question of how much, if you have if there is an EU ration card system, or if France and Germany are issuing ration cards, can Germany trust the French ration card, et cetera. So an advantage of these ring VRFs in that kind of context, as opposed to some kind of, anonymized certificate scheme, is that since we just have a public list that we're sort of accessing in zk, then it's actually much harder to have fraudulent certificates. So this is one thing where somehow blockchain-ish thing, or at least maybe not a blockchain, but access, using the ring signature really gives an advantage in terms of managing the certificate infrastructure. Okay, one last thing. So I mentioned this Cards Against Humanity game, and so people have heard of these secret single leader elections. Okay, so it means that basically you want a block production scheme in a blockchain where the blocks come like every 6 seconds, some fixed time increment, and we don't know who the upcoming ones will be. So usually the way this is done is with a cryptographic shuffle. We have a much more efficient one it's much more efficient in the sense that because you can tune the security levels of the shuffles as much as you want, and usually they tune the security way down to get them to be efficient. So instead what we're going to do is we're basically going to, for block production, we're basically going to play Cards Against Humanity. We're going to, all of the people who want to make blocks are going to, or who are authorized to make blocks, are going to produce a bunch of ring VRF outputs, and then we're going to just sort them, and that becomes the block production schedule for some upcoming epoch. And it's literally playing Cards Against Humanity by, there's a number of details here, which we have a paper I'm not going to talk about, but yeah. So some advantages. So the disadvantage is that, of course, the network layer anonymity is a bit weaker than if you tune the security level of the shuffle way up, because at some point the shuffle just becomes a verifiable mixnet, but that's not what people do in practice because that's expensive. So advantage is it's very easy to analyze. So it's quite a bit more efficient than shuffles with the security tuned way up. Another advantage is that unlike with the shuffles, the block producers can prove their slot in advance, which is useful in some kind of multi-chain thing like Polkadot, where you want to have, where you have these parachains submitting to the relay chain. Another advantage is because we have a schedule. If we put an ED25519 key in each of those tickets, then we can actually set up things where users talk to the upcoming block producers over Tor, and then you don't need a mempool. That cuts out, that would cut out 50% of your signature verifications in the blockchain. And if you start using batch verification in the blocks, that cuts out, much more than at least 2/3 for ED25519 signatures. And if you're using ROS16 or something, that cuts out 90% or something of your signature verification. So that saves a lot of CPU, saves some bandwidth, and it also enables some better MEV defenses. I'm not generally a fan of smart contracts anyway. Anyway, that's what I want to tell you. One last thing. So in general, we do have some pieces, since we have a lot of students here, we do have some work going on around trying to get stuff done with VRFs and games, ring VRFs and games and other stuff. And if people are interested, they should talk to me. All right, that was a little fast.
Who has questions? I have a microphone and we'll give it to anybody who has questions. So I would like to ask the first one.
Yeah.
These ring VRF signatures, where are they currently deployed?
We haven't deployed them yet because I haven't done a really nice implementation yet. I've been screwing around and finding new tricks, and okay. We have it. We have not the one you saw here. We have not the Gras-16 proof. We have so there's a very optimized Planck proof. It's not Planck. It's a Planck-ish thing that we did for that we did for Burdges, which I'm not sure if Bhargav will talk about or not. But so Sergey and Alistair did this mostly, and there's a version of this Peterson VRF plugged into that, which is slightly more efficient for sassafras. So we have that implemented, basically just because the size of the block product, there's only 1,000 validators, so you actually don't need quite this Gras-16 thing I'm talking about for sassafras. So it's and because it changes every 6 hours, it's just slightly faster in total, because everybody only makes a few proofs. Okay, so that one is implemented and works and has run on test nets and things like this. The Gras-16 one, basically, I would like to hammer out some details, all of the details about how I'm doing the revocation stuff and things like that. But it's not actually that hard to finish. I just have to go and do it.
Okay, thanks. Yeah. Anybody else having questions? Yeah.
So just from my understanding about this last scheme, you're saying you can avoid the mempool. Is that because you can basically know to which block proposer you send your transactions to?
You don't know who they are, but because there's a list of tickets, you could publish a Tor onion URL in that list, and then just talk to that guy.
Okay, I see. Thanks.
And of course, this requires a lot of infrastructure. This requires you now have to use Tor. You now have to use this is not a simple thing to go and build, but it does save you quite a bit.
Yeah, sure. Thanks.